Okay. Fine. Okay, so basically temperature control system, there are two kinds of systems are there for the injection mold. Okay, heating system and the cooling system. Heating system and cooling system. Okay, so one system is used for heating the raw material and another is required for the cooling purpose. Okay, cooling of the heated component. Okay, now, so in the heating, as I told, a simple mechanism will be there. Heating coils are provided here around this barrel. Okay, these are the heating coils provided along this barrel, and slowly as material passes from this barrel, it will get heated. Okay, getting it. Okay, so heating, see, basically if you look after this two processes, this is not a complicated process, heating process. Getting okay, in the heating process, simply we are going for phase change from solid to liquid. Okay, simply a phase change. But most of these structural transformations occurs during cooling. What I am saying, structural transformations. Okay, so most of the structural transformations are observed during cooling and not during the heating. Okay, heating is, purpose of heating is only to change the phase, okay, from solid to liquid, to change the raw material from solid to liquid. Okay, so that is the only purpose of heating, and controlling of the heating is also simple. Okay, so most important role in the temperature control system is of the cooling system, because type of the product, quality of the product, uniformity of the product, everything is managed by this cooling rate or the cooling parameter, because structural transformation occurs during this cooling. Getting it? Okay, now what happens now in this cooling system, see, whatever the time of cycle is there, one by one we'll see the first point. Okay, time of cycle means what? Entry of raw material, exit of component. Getting it? Okay, so this complete entire cycle time. So out of this entire cycle time, 70% to 80% time is required for cooling. Okay, so around 70 to 80% timing is taken by this cooling process. Okay, if you are not getting the screen, just zoom it. Okay, you will be able to see it properly, or I'll increase the pen size also. Getting it? Okay, so around 70 to 80% time is required for cooling purpose, out of total cycle time. Okay, so that is most important in case of the product quality. Now see, now we'll see some basic things. Now suppose let first of all the material is in a heated condition. Okay, so and then you start cooling the particular material. Now what happens, there are three kinds of cooling rates are there: fast cooling, or it is called as rapid cooling also, moderate cooling, and slow cooling. Okay, slow cooling. Okay, so fast or rapid cooling, moderate cooling, and slow cooling. Now what happens, if you employ any of this cooling rate, so there is going to be the change in the microstructure. So moderate is nothing but when you want the hybrid structure, which you will get in the fast and slow cooling. Now what happens, when you will cool any material very fastly, when you cool it very fast, so fine grain structure is produced. What type of structure? Fine grain. Fine grain in the sense small grains. Okay, and when you cool it slowly, then coarse grain structure is produced. Coarse grain in the sense large size granules. Large size granules. Are you getting the basic thing? Okay, this you might have studied it in your metallurgy also. Okay, moderate is not required. Fast or rapid cooling, fine grain. Slow cooling, coarse grain. Okay, and that will decide the properties of material, properties of component. Okay, quality of the component. Getting it? Okay, Another one thing, if you heat it very fastly, sorry, if you cool it very fastly, or rapid cooling will be there, there is a possibility of residual stresses. There is a possibility of residual stresses. What happens when you cool the material slowly? The material will get time to relax. Okay, in simple language you'll understand. Material, when you will cool any material slowly, material will try to get relax, material will get the time to relax. Okay, whenever it will get the time to relax, this residual, see, this stress and relax are opposite to each other. This stress and relax are opposite to each other. Whenever material will have good time to relax, stresses will not be there. That means if cooling rate is slow, residual stresses will not be there. Residual stresses will not be there. Okay. So there are some pros and cons for each and every process. Okay. Just a minute. Right. Okay. So second point is regarding residual stresses. Whenever you will cool it very slowly, residual stresses will not be there. But if you cool the material very fastly, if cooling will be very fast, then residual stresses will be there. Okay. And you know that if residual stresses will be there in the component, possibility of crack generation will be more at that particular point. Okay, possibility of crack generation will be more at that particular point. Okay, second thing, this happens when there is a fast cooling. Again, if you look at the uniformity of product quality, uniformity means what? Suppose this is the product, there should not be voids, there should be uniform density of the product. Uniform density, when it is possible, when it will be uniformly cooled at each and every location. When voids are not possible, when there is a uniform cooling rate at each and every location. When there will be fast cooling, is it possible to get proper cooling rate throughout the system? No. Right. So whenever there is a fast cooling, this is not possible. Uniformity of product quality is not possible when fast cooling will be there. Getting it? Okay. So if you want the fast cooling, sorry, if you want the good product quality, not that much slow cooling, but at least it should not be a fast cooling, right? So again, because see, ultimately this cooling will have impact on shrinkage rate, and shrinkage will automatically manage these things: residual stresses, uniformity of product quality. Getting it? Okay. Density, uniform density of the density. Okay, this everything is managed by shrinkage rate. Rate is nothing but the cooling rate. Getting it? Okay. So as 70 to 80% cycle time is invested in the cooling mechanism or the cooling system, we should take care about this residual stresses to maintain the uniform product quality and to have the uniform shrinkage rate. Getting it? Okay. So that cooling is more important rather than heating mechanism. Okay, rather than heating mechanism. Right. So now see, cooling, there are so many cooling medias, okay, that are not part of our syllabus. But if you will study it in a metallurgy, there they have discussed in a detail. Okay, like air cooling is there, oil cooling is there. Basically, this process is called as a quenching. In metallurgy, this is called as a quenching. Okay, so air cooling is there, oil cooling is there, oil bath or water bath, anything. Getting it? Okay. So this cooling rate will depend on this cooling media also. It depends on the cooling media also. That is called as a quenching media. Right. So that this temperature control system, in the sense a cooling system. In other, I can say this is a cooling system, because heating system is not that much important. Cooling plays a major role in case of the quality of the product. Getting it? Okay. Another one important factor is there. Two things are there: fast cooling versus slow cooling. Now if I will go for a fast cooling of the component, in the same period I will have more number of products. Simple thing. Okay, so if cooling will be fast, production rate is going to be a more, so more number of products. But if cooling will be slow, it will take too much time, cycle time will increases, and number of products will decrease. Number of products will decrease and in case of fast cooling, number of product will increase. Okay, so see, somewhere you will have to have the middle way, getting it. Okay, if you employ the fast cooling, production rate will be more number of quantity of product you can go for, but uniformity will not be there, residual stresses will be there, getting it. Okay, so pros and cons for both the process. Okay, so this is one more factor that if there will be a fast cooling, more number of products can be manufactured. If slow cooling will be there, less number of products will be there, getting it. Okay, so this is what about the temperature control system. Okay, so these many parameters are important: quality of product, residual stresses, shrinkage rate, and production rate, getting it. Okay, and what is there another? Now see, quality of product, in the sense there are so many parameters are there. Quality of the product, small surface quality. Okay, then internal quality means what? Strength of the product, density of the product, no wides, okay, no open spaces. Internal quality. Okay, so quality in the sense so many factors are considered, getting it. Okay, so these many parameters are there in the temperature control system. Now next is the, what is next? Okay, so this is the temperature control system. Next is the ejection system. Okay, so first of all, basic parameter we'll take, and then we'll go for the types and feeding mechanism, etc. Okay, so then next one is ejection system. These are basics and common for all kind of process. Next one is a ejection system. Okay, so ejection system we have discussed in a detail in compression molding also, right? So in the compression molding also, but we have discussed about the design of ejector also, pin type ejector, but here we'll see more types of ejector systems. Okay, basically ejection system is nothing but one very nice word we discussed in compression molding: bouncers. Okay, so these ejectors are acting as bouncers. So role of bouncers is to remove the product from the mold, from the mold cavity. If suppose this is the mold cavity, and if this is the product inside this, okay, this is the simple rectangular product inside this. So from this side we'll have some pin type of ejector, okay, which will push this product out of this. Wait a minute, I lost my connectivity. Right, okay, so this roll off ejector is a, will act as a bouncer. Okay, so to remove the product from the mold cavity, getting it. Okay, so basically there are different kinds of bouncers, sorry, ejectors. Okay, so one by one we'll discuss in a detail. Okay, so first one, a popular one, a pin type ejector. Second one, sleeve type ejector. Pin type, because we discussed only about the pin type ejector in the compression molding. Next is wall type ejection system. Fourth is ear type ejection system. Ear type ejection system. And fifth one, stripper type. Getting it? Okay. So first one, pin type ejection system that we discussed in a compression molding. Second is sleeve type injection system, sorry, ejection system. Then wall type ejection system, ear type ejection system, and stripper type ejection system. Okay. So basically there are 5 different types of ejection system. Okay. Not all are used at once. Okay. Depends on the type of product, type of mold, wall thickness, size of product, height, sorry, weight of product. Getting it? Okay. So so many parameters are there which will decide the type of ejection system required for the injection molding. Okay. So the basically 5 types are there: pin, sleeve, wall, ear, and stripper type. Pin, sleeve, wall, and stripper type. Okay. So now the first one will be pin type ejection system. Okay, we'll see one by one. So here it is, pin type ejection system as shown. Okay, so I'll once again draw this. Why it is not taking color? Okay, so this is, sorry, this is the product. Now don't look at the entire figure. This is the simple product manufactured through the injection molding system. Okay, this is the simple product. Getting it? Okay, so now I have to remove, see, we'll go in by the reverse engineering way. Getting it? Okay, so now we are discussing a pin type ejection system. Pin type ejection system, right? Now a simple product. Now if you look at this, the base of the product, this surface, this one here I am marking, this one, this surface, this one, and this one. Okay, so we are having two options: either to push the product from these locations, these two locations, or to push the product at the center, from the center. Rather than going for these two pins, this one and this one, I can go for one central pin here. Getting it? Okay. Now but the thing is that, first of all, see, if you push from this side, if you push from this side, you need to have less length of pin. Okay, because you are pushing from this base. If you will push from this base, this one, you need large length of, sorry, larger length of the pin, first of all. Second thing, this complete length of the product is more, and if such kind of length of product will be there, and if you are pushing it at the center, if you are pushing it, or if you will try to push it at the center through some pin which is having a less area, less surface area, so it will try to pierce. Are you getting the meaning of pierce? Okay, indent. Okay, it will try to go inside the surface, inside the surface, or rather there is a possibility of buckling. Are you getting? At the start the product is straight, but because of this pressure at this end, sorry, at this center, there is a possibility of buckling or the deflection of this particular component. Getting it? Okay, so that, what is preferred here, rather than going for this kind of pushing, it is preferred to have the push from this side, one at this base, another at this base. Okay, what will happen with this? See, as we are using, two pins, one at this side, one at another this side. Okay, the pressure required, or the force required to eject the product, will be less. Force required to eject the product will be less, and whatever force we will apply, it will be distributed over two pins, half of the force on this, half of the force on this. Okay, so at particular location there will be less force, and that's what the aim is there. Because see, This is the surface. If we will try to push, if we will try to centralize the entire force at one location, this pin will try to pierce inside this surface. Getting it? Okay. So try to manage the forces applied. Getting it? Okay. So in this case, force will be, or the pressure will be distributed properly. Okay, at these two locations. So piercing will not be there, and we can easily remove the product or eject the product out of the mold cavity, right? Now in case of pin type ejectors, mostly, if this is the wall thickness of the mold, so that much size of pin, diameter of the pin, don't get confused, I will show it here. So this diameter of the pin here, this diameter of the pin is same, preferred as same of the wall thickness of mold. Getting it? Okay. So because see, suppose this is the mold wall thickness. Okay. Just take the simple example, and I am using a simple small size pin. What will happen when it will try to go inside this mold? It may try to buckle or deflect. Getting it? Okay, because size of this wall thickness is more and the size of pin is very small. Getting it? Okay, so try to keep the diameter same as the wall thickness. That's what the intention to discuss here. Getting it? Okay, so this is the pin type ejection system. This is the pin type ejection system. Getting it? Okay, so sorry, so don't prefer, 2 3 points will revise. Don't prefer a very small size pin, it will pierce inside the surface. Don't prefer so much large size pin. Getting it? Don't prefer so much large size pin, because large size pin will require large force also. Getting it? Okay, large force also. So that is the thing, so that optimum diameter of the pin is preferred rather than going for the small or large size, right? And one more issue we discussed in the compression molding about the surface of the pin. Okay, so just see here, it should not be like this always, a plain surface. Okay, now see here, you can prefer plain surface, but if your product is like this, a spherical shaped. Getting it? Okay, so area of contact by using this kind of pin will be less, so you need this kind of pin for the cylindrical surface. See, I will show it to you. Got it? Right? So this kind of surface at the tip of the pin, so what will happen? Because of this surface, you will have cylindrical component. So surface contour and your pin contour will be exactly matched. Are you observing now? Okay, so if you will match, if the alignment will be proper, requirement of force will be less. That's what I want to tell. Okay, getting it? Okay, so this is called as pin type ejection system. This is called as pin type ejection system. Getting it? Okay, now second is sleeve type ejection system. Second one, I'll write the name, sleeve type ejection system. Okay, now these types are because of the type of the product. Simple. Okay, so first of all, understand the product. If product is of this type, I'll once again show it to you. Hollow product. Are you getting? Hollow product. Now this is the outside dia and this is the internal dia. Okay, hollow product. Okay, now What is the problem here to use the pin type ejection system? Where to place the pin? If I'll try to place the pin here, how to place it here? Or if I'll try to place it on this surface, where? On this surface, on this solid surface. Check out the area, surface area. This is very less. This is very less. So I cannot keep one pin at this side and one pin at this side. Getting it, right? So this is a totally a different kind of product. Okay. So this kind of products where there is a, or where products are hollow, where products are hollow, so surface area, effective surface area is very less, so we cannot go for the pin type ejection system. So we are having sleeve for that purpose. What is the sleeve? Here it is shown. A bar, or you can say a different cross section, but with different size in one piece. Now check this one. Okay, this one. So this surface, this much part, I'll show it with the different color. Getting it? Okay, only this much part, only this much part will enter in this cavity or in this hollow area, and this two, this and this will rest, one will rest on this, another will rest on this. Are you getting? Simple panda. This elongated part will go inside this hollow area, and this two surface will rest on this side area. Okay, and you can easily eject the product. You can easily eject the product. So your question is, your question will be, why there is a not why there is a like this uniform section rather than this step section. Okay, so this is because you can use same kind of sleeve for the different kind of product with the different diameter. If diameter will be less, sorry, diameter will be more, this cross section can be used. Again, more diameter, this cross section can be used. Okay, currently we are using only this surface. Getting it? Okay, only this surface, first one. So this will go inside the cavity, inside the hollow area, and this one will rest on this two side surface. Okay, and you can easily remove, or you can easily eject the product from the cavity. Getting it? Okay, so that's what the sleeve type ejection system. Sleeve type. Are you getting? I'm not giving too much time because this is a very simple things are there. Right. Okay. So if hollow component, if hollow component prefer sleeve ejection system, right? Next one is a wall type. Next one is wall type ejection system. Okay, so this is the product, this one, this larger one. Okay, and now if you can check the size of the product, thickness is looking small, but check the size of the product. Okay, so size of the product is very large. So whenever there are large size component, large and deeper component, deep in the sense, see, very large size and very deep also. Are you getting? In such cases, see the depth, this much depth is there. Okay, so in case of large and deep components, this wall type ejection system is used. Wall type. Okay, so this is a simple wall which is resting on the surface. Okay, this is not a pin type, this is the pin. See, up to this is the pin, this is the pin, but at the surface of the pin, valve is attached, a rubber wall or another one material you can use. This wall is there. Okay, so what is the purpose of this wall? this wall will rest. I'll give you simple example. Have you seen the large size cranes? Okay, if you have seen the large size cranes, so when you want to pick up a very large component by using large size cranes, they are not using the chains or angles like this, holders or clamps. They are not using this kind of clamps or holdings, okay, to pick up by using the crane. Okay, rather what they are doing, very simple example I'm giving. If there is a very large size component, what they are using, they are using magnetic based lifters. So what they are doing, a magnetic based component is kept on this surface. It will stick to the component and it will pick up the component. Same process in the reverse way is used here. Are you getting? Because large size component, if you will try to pick up by using the hooks or by the chains, it will buckle or it will have the deflection here. Okay, same thing is possible in case of large size component here also, if you use the pin type ejection system. Okay, pin type ejection system, so that this, what is the intention, only the large size area is provided at the tip. This large area is provided at the tip. And now see, if large area is provided, we need some mechanism to push it, and this spring back mechanism is provided. Okay, so this wall will rest on this surface, large size surface, and it will push the component out of the mold cavity. Okay, by using the spring, this pushing and pulling back the wall, this pushing and pulling mechanism is operated by using this simple spring mechanism, spring back mechanism. Getting it? Okay, so this is called as a wall mechanism, or sorry, wall type ejection system. Wall type ejection system, preferred preferred when there are large size component, preferred when there are large size components. Okay, now the next one is ear. This is wall type, wall size used for large and deep component. This one is ear type, ear type ejection system. Same as like wall type ejection system for large and deep component. Only thing is that here, I'll remove this one. Here you used spring mechanism to push and to pull back, and here what you are using, ear mechanism, compressed ear. Okay, compressed ear. When delicate components are there, obviously, see, this is a mechanical type mechanism purely. Okay, friction and all parameters are will be there. In case of air mechanisms, see, simple, this is simple as like your conventional braking system, and this is a air braking system where you are having the more accuracy, air braking system. Okay, similar way, compressed air will have, or the will be preferred more rather than this uh, spring type mechanism. Okay, so this, in case of this, similarly, here will be a wall. Okay, here will be a wall which is kept on this surface, which is supported on the surface, and this compressed air will push, this compressed air will push the component out of the mold cavity. Okay, so this is called as a air type. Simple mechanism, same as like spring mechanism, only the air is used, only the air is used. And the last one, quite different but same purpose, stripper type. Okay, this is also preferred when there are deeper components, deeper, having the high depth. Okay, spring mechanism, or you can use the ram mechanism also. So what is there, see, this is the component, I'm showing it with the red color. This is the component, and here is the cavity, here is the cavity of the component. Okay, so when there is a very high deeper component, so a similar kind of stripper is used, which will be exactly adjusted inside the cavity. which will be exactly adjusted inside the cavity. I will zoom it. Getting it? Okay, so which will be adjusted exactly inside the cavity. So this is the stripper. This is the stripper. Okay, so if you check the size and design of stripper is exactly as like the product cavity. So this stripper will go inside this cavity and will push the component out of the cavity, sorry, mold cavity. Okay, so this actually will not come back automatically. So here is the stripper mechanism, this one, this core. This core is holding this stripper. This core is pushing. Look at, from this side there is a pushing mechanism. This will push this core. This core will push this stripper, and same way as like spring back mechanism, they will pull back the stripper when the component will be stripped outside the out of the mold cavity. Okay, so after the ejection, stripper plate get back to the original position by this guided pillars. Getting it? Okay, so these are the guided pillars or the ejector pins. Okay, so this will guide the this stripper mechanism. Okay, so this is the stripper when it is preferred, when component is deeper. So these are the ejection system. This is stripper type, this is air type, this is the wall type, then sleeve type when you are having the hollow component, and this is the pin type. Okay, so basically there are 5 types of ejection system: pin type, sleeve type, wall type, air type, and stripper type. Getting it? Okay, and the cooling system, purpose of the cooling system will be uh, avoid residual stresses, maintain uniformity of product quality, proper shrinkage rate, and to maintain the production rate either by fast cooling, or if production rate requires lesser, you can go for the slow cooling rate also, right? So that's what for the today. Wait a minute.